Hello, my name's Jared Varney, and I'm one of the team members of this project. And thank you for coming to see our poster. So, our project, the little background on it, is Dr. Christensen is the director of nuclear engineering at the University of Idaho. And what he's doing now is he's trying to build a small scale nuclear reactor. And this nuclear reactor has a cylindrical core on the inside where molten salt flows from the bottom to the top. And right now, in his current design, there are recirculation zones around the bottom and top rim of this cylindrical core. Recirculation zones aren't good. They cause molten salt to stay there, and through all the different things that happen within a nuclear reactor, having stagnant molten salt there isn't good. And so what he wanted us to do was to design a sort of orifice plate, a filter, some sort of flow guide that is able to manipulate the flow through the core to have an even velocity profile across a cross section of the core to where all fluid is flowing upward, no recirculation zones, and we're able to get the most flow out of our core. Some required functions of what Dr. Christensen asked of us is that whatever we make needs to be visible to the naked eye. We need to be able to measure pressure drops. We needed to have dimensional analysis done on it. And we overall needed to eliminate or minimize recirculation zones. So to do this, we made an 1/8 scale model of the core, and it could be seen that we didn't do a pizza pie shape in a sense. We actually did a triangle shape. This was done to minimize manufacturing. We're able to get plexiglass or acrylic on all three windows for a triangle, and we didn't have to worry about bending a piece on that back side. That way we can get the most view of whatever's flowing through our prototype. We also were able to 3D print pretty much everything that was customized. We were able to CAD up different designs, and then we were also able to 3D print them on personal at-home 3D printers. We were able to drive down costs with this, and we were able to do iterations on the fly, which was really nice. So in the top left picture under models, you're able to see how we manipulated flow in a sense from a PVC pipe in a circular opening. We were able to split the flow out from a small circle to a large rectangle. And where the green transitions to red is where I guess the red triangle base would be representing the bottom of the core, to where after we have an orifice plate in there, you could manipulate the flow up and through the core. The bottom right picture shows our prototype all put together, and the blue, I guess you can call them edge pieces, stands, corners. Those, the white space in between, actually, that's where the acrylic would be, and we were able to see visual flow through those acrylic windows. At the very top, there's a rain gutter sort of system to help collect water once it's flown up and through to then recirculate all the water. The top right photo, or the top right picture, is an actual CAD model of our whole test bed. There's a cart, bucket, recirculation pipes, an angled manometer to measure pressure drops, and our prototype. After we're able to get certain dimensions down on our prototype, we're actually able to do CFD models. And these CFD models are just computational fluid dynamic models. And after putting in certain variables, we were able to see how we would expect the fluid behave. It's not perfect, but it was able to give us a good idea. So in the bottom left, those two pictures there, the far left just shows sort of a heat map, you could say, of the fluid flow through our core. On the bottom left of that picture is where fluid would flow in, and on the left side would be the outside rim of the core, and on the right side would be the center of the core. And so, as to what Dr. Christensen was saying, our CFD models match. Having no orifice plate, no filter, no flow guide, we're able to see that fluid flows and it all tries to collect towards the center, leaving the outside edges to have recirculation zones. The next picture in on the right, if you're able to zoom into that, hopefully you can, there are velocity vectors at certain points in our model. This was able to show what direction the fluid is trying to flow. And as you can see in the red zones and the yellows, fluid flows pretty normally. And in these blue zones on the outside, it's sort of chaos, at least in our models. So after 3D printing for several hundred hours, I think we had 200 to 300 hours worth of printing, we were able to have a final product. Under the final product section, that middle picture shows our prototype. Everything that's in white, other than those two, I guess you can't see the backside, but there are two PVC pipes coming down from our rain gutter system and PVC pipes coming into our prototype. Everything else was 3D printed. We have acrylic plates, acrylic sheets to view flow, and we also have an angled manometer mounted on a versatile mount to help keep it level with wherever the cart ends up being. On the right, that right picture, you're able to see what's underneath the cart. On that first top layer of the cart, you're able to see what's on the bottom level of the cart, which is just a bucket. On the inside is a pump that allows little tiny bits of debris to come through. They're usually used in aquariums, but we were able to use it and be able to get little polyethylene beads and ABS beads. These two different beads were able to help us get sort of neutrally buoyancy within our fluid, and we're able to see fluid flow, which was really nice. On the left are 4 pictures of about 7 to 10 different orifice plates we did make. These are just the main highlights, just showing how we computationally made different orifice plates. And the orifice plate that gave us the best solution was the bottom right picture, which under verification data you can see. On that left side is fluid flow, with the left side being the outside rim of the cylindrical core and the right side being the center. On the left picture, you can see fluid flow without an orifice plate. It matches our CFD models. It matches what Dr. Christensen was saying from the get-go. After using this specific orifice plate, you can see the velocity flow on the right side. These red streamlines, they show the direction that certain beads were traveling. Also, according to the height, it also shows the velocity. So overall, we were able to create a test bed that Dr. Christensen can use for the years to come while he's designing this current reactor. What we weren't able to do was we weren't able to get truly uniform flow. As you can see from that picture in the bottom right under verification data, there are tiny recirculation zones, and also the fastest flowing fluid isn't within 95% of the slowest moving fluid, meaning that slowest moving fluid, I think after our numbers were crunched, it was about 65% of what the fastest moving fluid was. So it wasn't exactly laminar, which was a hope of ours, and we weren't able to get fluid flow through the core exactly where we needed it to be. It's really hard to get these mimicked neutrally buoyant beads to flow under very low flow rates. But we were able to get something really close. Under these circumstances, we were able to provide very good data to Dr. Christensen. And yes, this is our project, and hope you like it. And thank you so much for taking the time to listen.